Today we're going to derive two nice approximating inequalities of n factorial. So the first one says that n factorial lies between the square root of 2 pi times n over e raised to the n power. So that bounds it from below. And then it's bound above by e times the square root of e times n over e to the n. So observe that this lower bound is in fact Stirling's approximation. So this can be seen as some sort of maybe companion result to Stirling's approximation. Okay, so let's maybe dive into this first one and then we'll look at the second one. Okay, so in order to start off here, what we're gonna do is look at the graph of the natural log function. So let's get the graph of the natural log function on the board. Let's recall that it looks something like this. So here I'll put this is y equals natural log of x. And now what I'm going to do is, well, look at this natural log function between two positive integer values. So let's maybe go ahead and put n right here, and then we'll just extend it out and put n plus 1 right here. So it's like we're zooming in on part of it. So making it not really to scale. Okay, so now I'm going to throw up a vertical line segment to here. And so that's clearly going to intersect the graph at the point natural log of n. And then I'll throw up another vertical line segment here until it intersects the graph. And that's going to intersect the graph at the natural log of n plus 1. And now I'm going to complete this into a trapezoid. Okay, so there we have it, completed into a trapezoid. And now, well, let's observe that we have the following inequality. So the area of this trapezoid, so let's just put a little picture of the trapezoid right here, is in fact less than the area under our function y equals natural log of x, where x runs from n to n plus 1. And so, well, that's because we've got a concave down function, and that makes the secant line lie completely below the graph. But assuming that you have that kind of thing happening, well, then you clearly have a smaller area based off of this trapezoid. Okay, so next up what we'll do is calculate these two areas, giving us an inequality. So the area of a trapezoid is given by 1/2 times the length of the base times the sum of the length of the heights. So that's going to be 1/2 of natural log of n plus 1 plus the natural log of n. And then, well, what's the area under the curve? That's exactly why we defined the integral. So this is going to be the integral from n to n plus 1 of the natural log of x dx. Then, well, I'm going to use logarithm rules to push these two things together on the right-hand side. And this is going to, in fact, turn into the natural log of the square root of n times n plus 1, bringing that half inside. And then, well, taking the integral of the right-hand side is not too bad. You might want to use integration by parts. But after doing that and making an evaluation, we'll end up with the following value. So it'll be n plus 1 times the natural log of n plus 1 minus n times the natural log of n, and then finally minus 1. Okay, so like I said, that's just done with a simple integration by parts. Okay, but now let's observe that we can put all of this stuff together on the right-hand side using logarithm rules again. So what I'm going to do is take this number 1 here, and I'm going to write it as the natural log of e. But that allows me to write the right-hand side as the natural log of n plus 1 to the n plus 1 over e times n to the n. So something like that. But then I'm going to rewrite that as the natural log of n plus 1 over e to the n plus 1 times e over n to the nth power. Just to group the e with the n and the n plus 1 term. So we have these two, similar objects being multiplied. Okay, great. But now let's observe we've got the natural log of this stuff over here is less than the natural log of that stuff over there. But then since the natural log is an increasing function, we can simply extract the arguments and pick up a nice inequality which looks like the square root of n times n plus 1 is less than n plus 1 over e raised to the n plus 1 times e over n raised to the n. And then the last thing that we'll do before we move to a clean board is write this left-hand side of the inequality in a way so that it looks, maybe a little bit more similar to the right-hand side. And, well, it will involve a factorial as well, because we shouldn't forget that our goal is to produce an inequality involving a factorial. So what I'll do is I'll take this and I'll write it as the square root of n times n plus 1 over the square root of n plus 1. And then from there, what I'll do is I'll multiply the numerator as well as the denominator by n factorial. But then I can group the n plus 1 and the n factorial in the numerator to an n plus 1 factorial. And that gives me the following inequality after I make a replacement. So I'll have the square root of n over n factorial times n plus 1 factorial over root n plus 1 is less than this right-hand side. So that's our n plus 1 over e raised to the n plus 1 times e over n raised to the n. Okay, so let's start with that and see where we can go. So here's where we are so far. And I'd like to take a look at this inequality and observe that there are terms inside of this inequality based with n and terms that are based with n plus 1. What I'd like to do is to consolidate each of those types on one side of the inequality. So in fact, what I'll do is I'll take this term right here, which I'll say is based in n, and I'll move it to the right-hand side of the inequality. Whereas I'll take this one, which is based in n plus 1, and I'll move it over here to the left-hand side of the inequality. Of course, when I move these things across the inequality, I have to multiply by the reciprocal, but I think that's pretty clear. So what will that leave us with? So we're going to have n plus 1 factorial times the square root of n plus 1. So this is happening on the left-hand side. And then we'll have what? An e over n plus 1 raised to the n plus 1. So that's from moving that peach-boxed term over to the left. We had to take the reciprocal. And then in turn, that's going to be less than, we have an n factorial over square root of n times e over n to the n. Okay, great. But now, observe that those two terms look exactly the same, except the one on the left has n replaced with n plus 1. So that motivates us to look at a sequence of numbers defined by this formula. So I'll call that sequence A sub n. So here we've got A sub n is that left-hand or that right-hand side. That makes A sub n plus 1 the left-hand side. And now, well, let's note the following kind of fairly obvious fact. And that is that we have 0 is less than an plus 1, which is less than an, which is going to be less than or equal to a1, obviously depending on what n is. But a1, well, you can pretty easily see that a1 is equal to the number e. So that means, well, what do we have? We have a sequence that's decreasing and bounded below. In fact, it's bounded above and below, but we'll mostly use the fact that it's bounded below to say that it has a limit. In other words, this sequence an converges. So let's sneak that in here. So an converges. Now, what does it converge to? Well, we're going to take care of that in just a minute. But observe that we know where it converges, or I should say we know an interval to which it converges. So we know the limit as n goes to infinity of a sub n is going to be equal to something called L, and L is going to lie between 0 and e. So we know it's going to lie between 0 and e. Well, based off of this inequality right here. But what does that mean? Well, that tells us the following. So for all n bigger than or equal to 1, or maybe we'll just say bigger than 1 here, we have L is less than AN, which is less than E. Okay, but then let's put our definition for AN back into this inequality, and we have L is less than n factorial over radical n times e over n raised to the n, which in turn is less than e. But from here what we can do is isolate the n factorial term, and we have almost everything that we need over here. So let's isolate that n factorial term and see what we have. So n factorial will be bigger than L times the square root of n times n over e to the n, but it'll be less than e times the square root of n times n over e to the n. So observe that this right-hand side is exactly our goal right-hand side. We just need to figure out this value of L to determine the left-hand side coincides with what we have over here. Okay, so let's finish it off with that fact. Okay, so this is what we've got so far. Recall that our goal was to finally determine the value of this limit L, where it's the limit of this sequence a sub n defined as on that right-hand side over there. Okay, so now what we're going to do is use something called the Wallace product. I think we've got at least one proof of this product on the channel already. And what it says is that pi over 2 in fact is equal to the following limit. So it's the limit as n goes to infinity of 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times, well, a bunch of terms ending at 2n over 2n minus 1 times 2n over 2n plus 1. So observe that all of the even numbers are occurring twice in the numerator, and well, up to 2n. And then all of the odd numbers are occurring twice, up to 2n minus 1, and then 2n plus 1 is occurring once. So in fact, we could put this together. Observe that this is the limit as n goes to infinity of, well, let's see, we're going to have 2 to the 2n. So that'll be what we get from factoring a 2 out of everything in the numerator, and then times an n factorial squared. That's because after factoring a 2 out of everything in the numerator, we have 1 times 1, 2 times 2, 3 times 3, 4 times 4, all the way up to n times n. In other words, n factorial squared. Well, in the denominator, we have 1 times 3 times 5, all the way up to 2n minus 1 squared times 2n plus 1. But now what I'll do is I'll slide all of the even numbers in here. So I'll put a 2 here, I'll put a 4 here, all the way up to putting a 2n at the end there. So what does that end up leaving me with? Well, in fact, that leaves me with another copy of 2 to the 2n times n factorial squared up there in the numerator. And then in the denominator, well, I can push all those together to 2n factorial. So let's do that as we copy this down. So the limit as n goes to infinity of, so this is going to be 2 to the 4n, and then we have n factorial to the 4th, all over 2n factorial squared times a 2n plus 1 in the denominator. But now what we'll do is, well, I'm going to take this 2 right here and move it over by just multiplying by 2 in the numerator on the other side. So I'll just put that in all of those. And then this gives us this nice formula for a limit involving the square root of pi. So that'll be taking the square root of both sides. So we get the square root of pi is the limit as n goes to infinity of 2 to the 2n plus 1/2. We get that from putting the 2 to the 4n and the free 2 on its own, times n factorial squared over 2n factorial times the square root of 2n plus 1. Okay, so now let's see what we can do with this limit. Okay, so this is where we just ended up. And now what we'll do is take this equation, this defining equation for a sub n, and, well, we're going to solve it for n factorial. So that's going to give us n factorial is equal to, well, that's going to be the square root of n, or I'll write this as a sub n times the square root of n times n over e raised to the n power. And then what we'll do is we'll put that into our equation right here, or our limit right here. So I'll replace n factorial with that over there, and then 2n factorial with its companion. And then after doing, some simplification, which isn't so bad, we get the limit as n goes to infinity of a sub n squared over a sub 2n times the square root of n over the square root of 2n plus 1. Okay, but now let's observe that since we know the limit as n goes to infinity of a sub n equals L, that means we can take this limit very easily. This numerator goes to L squared, this part of the denominator goes to simply L, and then this quotient goes to 1 over the square root of 2. So in the end, this whole thing goes to L over the square root of 2, meaning that L is equal to the square root of 2 times pi. But check it out, if we take that L equals square root of 2 times pi and put it into the inequality that we had before, we achieve exactly what we were trying to. Okay, so now let's move on to this second inequality. So for our second inequality, we'll show that n factorial is bound below by n plus 1 over 3 raised to the n power, and above by n plus 1 over 2 raised to the n power. Okay, so what I'm going to do is build like an inequality which will be used as a tool. So I'll start with 2 and observe that I can write 2 as 1 plus n times 1 over n. Well, I think that's pretty clear. But then observe that that's going to be less than 1 plus n times 1 over n plus n choose 2 times 1 over n squared plus all the way up to n choose n times 1 over n raised to the n power. Well, of course that's true because I just added a bunch of terms that are positive. I guess here we're assuming that n is strictly bigger than 1. Okay, well, where could we go from here? Well, I'm going to smash all of this together into something that'll make it look a little bit more familiar, hopefully. So this is the sum as k goes from 0 to n of n choose k times 1 over n raised to the k power. But that looks exactly like a binomial expansion formula. It looks exactly like we've taken 1 plus 1 over n and raised it to the n power. But now I'm going to expand that back out. Essentially, I'm just going to rewrite this again, but I'm going to take these n over k, or n choose k, and write it out using its definition. So that's going to be n times n minus 1 times n minus 2, all the way down to n minus k plus 1, all over k factorial. But I'm going to put the k factorial over here, and then times 1 over n raised to the k power. But I'm going to split those 1 over n's and put them underneath each of these. But now let's look at this. This n over n is equal to 1. This n minus 1 over n is less than 1. This n minus 2 over n is less than 1. All the way up there, that n minus k plus 1 over n is less than 1. So we could just replace all of those with 1 and we'll pick up an inequality. So I'm going to do that and simultaneously make this into an infinite sum. So this is less than, the sum as k goes from 0 up to infinity of 1 over k factorial, which is defined to be e. But then let's recall that e has an approximate value of 2.718. That's most definitely less than 3. So moving forward, which portions of the inequality do we need here? Well, we're going to take 2 is less than this 1 plus 1 over n raised to the n power, which in turn is less than 3. So let's see what we can do with that. Okay, so this is where we were. And now let's massage this a little bit. So let's observe that this means that 2 is less than n plus 1 over n raised to the n power, which in turn is less than 3. I just put that stuff together that's inside of the parentheses. But now, what can I get from there? Well, notice I get the following thing pretty quickly, and that is 2n is less than n plus 1 raised to the n over n raised to the n minus 1, which in turn is less than 3n. So let's observe that this inequality has the seeds for some sort of telescoping action inside of it. That's because here we have an n plus 1 to the n, here we have an n to the n minus 1. Let's in fact take this and write maybe all the smaller inequalities, in other words, the ones where we replace n with n minus 1, n minus 2, all the way down to 2 and 1. So replacing n with n minus 1 here, we get 2 times n minus 1 is less than n to the n minus 1 over n minus 1 to the n minus 2, which in turn is less than 3 times n minus 1. And then next, we'll have 2 times n minus 2 is less than n minus 1 to the n minus 2 over n minus 2 raised to the n minus 3, which in turn is less than 3 times n minus 2. Now that goes all the way down to, the ground. So the case when n is equal to 2 and then 1. So we'll have 2 times 2 is less than 3 squared over 2 to the first power, which in turn is less than 3 times 2. And then finally, the n equals 1 term says that 2 is less than 2 to the 1 over 1 to the 0, which is less than 3 times 1. But now let's take the product of all of those and see what we get. So on the left-hand side, we'll have 2 to the n power. So that's from all of these 2's. So 2 to the n power times n factorial. That's from the n times n minus 1 times n minus 2 and so on and so forth. And then in the middle, we're going to have n plus 1 to the n over n to the n minus 1 times n to the n minus 1 over n minus 1 to the n minus 2, all the way down to 3 squared over 2 to the first times 2 to the first over 1 to the 0. And then finally, on the right-hand side, we're going to have 3 to the n times n factorial, similarly to the left-hand side. Okay, but then observe that we get this telescopic action in the middle. So this n to the n minus 1 will cancel this n to the n minus 1. This n minus 1 to the n minus 2 cancels the thing that comes after it. This 3 squared will cancel something that comes before it. And then this 2 to the 1 will cancel this one that's right after it. And, well, what does that leave us with? So we'll have 2 to the n times n factorial is less than n plus 1 raised to the n, which in turn is less than 3 to the n times n factorial. Now, let's take this compound inequality and pull it apart into two inequalities. So we can pull this apart and we'll end up with n factorial is less than n plus 1 over 2 raised to the n power, dividing by that 2 to the n. Then we can take the right-hand portion and we'll end up with n factorial is greater than n plus 1 over 3 raised to the n power. But then we can glue those two inequalities together back into a compound inequality, which looks exactly like what we were going for. And that's a good place to start.